Yeah, I wanted to introduce Víctor Chávez. Victor is a graduate student in Adam Wasserman Group at Purdue University, where we worked together for a long time until very recently, while I was also Adam's student. So at Purdue, Victor works on fundamentals of uh, embedding density embedding methods, in particular partition density functional theory. So that's probably will be the topic of his talk today. Um, like one of the recent projects of Victor's that I'm familiar with is establishing or like an adiabatic connection formula for fragments within density embedding methods. Victor also does a lot of very useful work of actually implementing a lot of those density embedding methods so they can be easily and readily available for the community. And finally, I just wanted to mention that he also focuses a lot on teaching aspect of quantum chemistry. He actively contributes to Psi4 education. It's one of the outreach branch of the Psi4 project. Also notably, Victor has a fellowship for Psi4 for the development on partition DFT and implementing Pdft within Psi4 computational package. So his talk today is called, I wrote it down, it's called Towards a Density Functional Theory of Molecular Fragments. We'll talk about DFT that's dealing with the dividing system into localized fragments. And I'll stop here and let him take it away. Thank you.
So thank you so much, Jan, for the introduction, and thank you so much, Dr. Neepa and Dr. Lionel, for allowing me to share some of the work that we do with Adam here. So today, I'll be mainly focusing on doing a small review on partition density functional theory, which is yet another flavor of embedding methods using density functional theory. So I'm just going to briefly go over some of the main aspects that we would want if we wanted to build a molecular theory of molecular fragments, of course, particularly density functional theory. So I'm going to start with this question, which is, what is the shape of atoms in a molecule? And of course, this is not a question with like a very good answer, but I'm gonna briefly bring the water molecule here with its molecular density. And what I mean when I say that this molecule is composed of an oxygen and 2 hydrogen atoms, what I really mean is that if I supply an appropriate amount of energy, I will be able to get the isolated atoms, being the oxygen and the 2 hydrogens. Of course, when they're in the molecule, individual atoms don't really have like a real independent existence, but we can sort of like think about its composition. And what we know about this thing is, of course, the sum of these spherical densities, of course, do not equal the molecular density. Otherwise, our chemistry would be ridiculously easy. But what we do know is that, this is not a bad place to start. There are approximately the sum of 3 spherical spheres. And I do know that if I apply the right distortion to each of these individual densities, here I'm considering atomic ones, I'll be able to recreate the molecular density. So although the question is a little bit vague, it is not entirely meaningless, because we can say that all of the molecular information can be encoded into a set of atomic or fragment distortions. So before I go further into more of this theory, what I'm going to say is that of course, here we fragmented based on the atoms, if nothing really prevents us to choose any other type of fragmentation as long as the external potential is recovered at the end. So I'm going to briefly cover some of the fundamentals of DFT, just because I'm going to draw some comparisons with DFT and partition density functional theory. So of course, we are interested in solving this type of electronic Hamiltonian. And from Huckenberg and Kahn, we know that any property can be calculated as a functional of the density. And then what we do is, of course, we have this energy functional that we split into the external potential part and then the universal functional that from Kuhn and Sham, we know that we can rearrange the true universal functional into set of things that I know. And okay, so we have the kinetic part and then the Hartree part, and then all of the things that I'm missing from having non-interacting electrons is going to be stored into this extra term, which is the exchange correlation energy. And then what we do in practice is, of course, each of those components, we apply a functional derivative so that I can build the Kohn-Sham equations to find the electronic density from the occupied orbitals. All right, so now, so of course, even though we are all very familiar with density functional theory, there are some instances in which we are a little bit unhappy with the performance of density functional approximations. Of course, we know that DFT is exact, but once we start applying approximations, that's when things go a little bit bad. And we know that this mainly happens whenever we're stretching a bond. And this is fundamentally due to the inability of the DFAs to reduce molecular densities to the correct atomic densities. So here I'm going to be using some examples for the local density approximation LDA, but of course this applies to any density functional approximation or most of them. So I'm going to start introducing the binding energy curve for the H2 plus molecule that is going to help me to describe a little bit of the fractional charge error. So here I'm comparing the exact calculation versus the LDA. And of course, we know that this molecule is 2 protons plus 1 electron. And we know that as we stretch the molecule, we should be having half an electron on the right and half an electron on the left because of left-right symmetry. And of course, whenever we split, we know that the real physical system will just behave as a proton on the one side and then a hydrogen atom on the other one. And the true density functional should be able to have the same energy for these two systems. And this is something that DFT, or at least in this case, LDA, is not able to correctly do. And this leads to the well-known delocalization error that Benjamin was talking in his talk. And then on the other hand, we also have the fractional spin error that in this case, I'm going to be talking about now the H2 molecule. And now in this case, the first part does not apply. And this is because, of course, when I stretch the H2 molecule, I now have 1 hydrogen on the left and 1 hydrogen on the right. Nevertheless, what does happen is that as we stretch the molecule, we know that the full molecule in its ground state is spin unpolarized. But as I stretched it without any extra perturbation, it should stay like that for a while. And then the problem is that the separated atoms, of course, are spin polarized. So just like we had a similar problem with the fractional charge error, we know that those two states should have the same energy in which LDA is unable to reproduce, and that's why we end up with these things. So the idea here is, of course, that based on the assumption that this problem happens because DFT is unable to reproduce densities that are separated, then a DFT theory of molecular fragments should be able to help us in some way. So what do we need when we are building an atomic densities as main variables? So I'm going to bring back the H2 molecule, and we start from what we know. So I know that I should be able to do Kohn-Sham DFT in each of the isolated fragments. And what I'm really interested in here is that I want to be able to minimize the fragment energy with the constraint that I have, or I retrieve the molecular density again. Of course, at the beginning, I said that I am doing quantum DFT on each of the fragments, but having this constraint here does modify a few things. So isolated fragments should be the true ground state of the external potential for each fragment. But once I add this extra constraint, I will find that in order to have the true ground state, I'll be needing this extra component, which is the famously known embedding potential, or in our work, we call the partition potential. And this leads us to the partition potential theorem. That is the basis for partition density functional theory, in which we just say that whenever we're fragmenting the external potential into a set of atomic or fragment densities, then if we fix fragment occupation, there's going to be a unique potential Vp that whenever we add it to each of the individual fragment potentials, we're going to lead to the ensemble ground state density that indeed will sum to the total correct N of R. And then just like I'm going to do an analogy with quantum DFT, because in quantum DFT, what we're doing is we're talking about not interacting electrons. And then I'm just looking for the exchange correlation energy that's going to, bring the energy to the correct one. So in here, instead of considering non-interacting electrons, we're considering non-interacting fragments. And then EP is the one who is in charge of bringing that missing energy. So now, of course, I want to briefly go through that sentence that was in the partition potential theorem, because I'm talking about ensembles, and our definition of partition DFT means that the only thing that I need is that each of the fragment number of electrons should add up to the total number of electrons. But this allows me then to have fractional electrons for each of the fragments. And this is, of course, allowed because we can have an interpretation of DFT through the means of an ensemble. So as we were seeing in the previous talk, we have the number n alpha for each of our fragments. And then what we're going to do is we're going to do a linear interpolation between a system that has alpha electrons and then alpha plus 1 electrons. And then we're going to find that the energy and the density is going to be given by that interpolation while we choose the omega parameter. Okay, so now I'm just going to briefly go through a simple illustration of Pdft so we know how everything works. So what I'm going to start doing is I'm going to introduce a system in one dimension that is just going to be composed of two particles that are producing this potential well. Then what I can do is I can do normal quantum DFT, and I'll be able to find the molecular density. Now, of course, our objective is being able to do calculations on each individual fragments. And what we do to start is we do quantum DFT on each of the molecular fragments. And then, of course, we find fragment densities. And just like we saw at the beginning, these two things do not add up to the same thing. But from the partition theorem, we now know that there is this external thing that I can add to each of the external potentials. Here, this is the VP that mimics very much the overlap region, but this is the orange one. I know that when I add this VP to each of the external potential, I'm going to modify that external potential in such a way that now each of the fragment densities will add up to the true ground state density. And here, this density is not changing by a lot when I add VP, but we can start to see some interesting behavior happening. So the purple one that has the dashed lines is a little bit on the left, and then the density that has been affected by VP is a little bit on the right. And then here, the difference between these is like kind of small. So what we do is just amplify that. And what we can see is that after I've added VP, I can see that the density shifts a little bit towards the bonding region. So this is what happens when we say in Pdft that the VP, or in the Venn potential, is the glue for the atoms in the molecule. So here, what I did, of course, was I just brought you the VP and told you, okay, this is what happens. This is what you need to build your theory of molecular fragments. But this is obviously easier said than done. So here I'm gonna go briefly over the algorithm that we can use to find the true partition potentials given a density functional approximation. So what we're gonna do is we're gonna choose our DFA, and then we're gonna solve the Kohn-Sham equations for each isolated fragments. So of course we have each of the external potentials that lead to the individual densities for fragments. And then what we're gonna do is we're gonna mimic, or we're gonna try to build, the molecular density. And this is of course not the true molecular density, but what we have to do is we have to compare the effective potential that is generating this sum of fragment densities. And of course, we have no access to that because we built this density as a sum of other things. So of course, what I have to bring here is an inversion, this is very much related to what Benjamin was talking in his previous talk. And this is because I want to be able to generate a correction for these external potential, or this effective potential. And what I can do is I just can compare the previous inverted Kohn-Sham potential with this other term. And given that I know that the true ground state density belongs to this external potential, I know that the difference of this will help me guide each of this BS sub alpha to lead to the real density. And of course, I'm just writing down this thing in a single line, but I could talk about for hours on how hard this is to do, and how inversions, whenever you're applying them with a basis set, you end up with a lot of spurious artifacts that are due to basis set expansions. And then let's just assume that everything nice and happy. Then we can just keep doing that procedure over and over until, again, hopefully self-consistent C will be achieved. And then each of the fragment Kohn-Sham potentials will be given by this expression. And then this thing that I'm adding at each iteration is simply adding to be the last VP. And of course, just like we oftentimes we see in Kohn-Sham DFT, we're interested in knowing what features appear in the true or the exact Kohn-Sham potential, so that they help us generate new approximations for this thing, because obviously this inversion procedure is actually, well, at least not cheaper than Kohn-Sham DFT. So right now, if I tell you that the objective is to have linear scaling, the fact that I still have this inversion procedure, of course, makes that not possible. So here, what I'm going to focus now is some of the features that we can find in the partition potential. And from our simple example, we can see that, of course, it has an attractive well in between the nuclei, and this distorts the density pulling towards bonding region. But this is, of course, just a one-dimensional problem that may not translate well into real molecules. So here, I'm just going to briefly go through some real exact partition potentials for the local density approximation. And here we can start to notice other features that we can get from the partition potentials. And except for the H2, we can see that normally you have positive plateaus due to kinetic effects that are these regions. And we've seen, at least with these examples, that the partition potential is mainly guided through the kinetic effects. So we're going to see how the decomposition of the partition energy is, and then we're going to see that the kinetic part is a main contributor in the overall shape of this. And then we also have the singularity of the nuclei, and we've also had some exact conditions that are based on the Cato's cusp condition. So the idea is that we want to gather as many exact conditions of this potential so that we can build better approximations for it. So when I first introduced the slides with errors in the calculations, the idea is that I would at least propose or give you some feedback on how we could improve this. And one thing that we can know is that whenever we are using a density functional approximation, we're actually recreating the Kanshan density. So that means that we are also recreating each of the errors that Kanshan DFT has. So what we can do is we can decompose this partition energy, just like how we do with DFT. And here we have the definition of EP. And just like we had with the EXE, we have kinetic, Cartesian, and external components. And this is something that right now we don't like, just like how the adiabatic connection initially was unhappy to have kinetic and potential contribution to EXE. So this is one of the motivations that we're working on the adiabatic connection for this part. And of course, we know the exact dependence on the external functional. So that means that if I remember those plots that I showed at the beginning, if I want to be able to fix the behavior when the molecules are separating, I can try to identify which of these components is being in charge of generating those errors, and then individually targeting those components so that we can easily manage those things. So here what I'm going to do is I'm going to briefly go over how can we approximate some of these components. And the group proved a few years ago that you can just simply do a simple overlap approximation that will fix those two errors. And this was done by having this non-additive exchange correlation functional. And here I'm using non-additive for each of the previous terms that I defined, which is just the difference between the real molecule minus the sum of the fragments. And then here you can see that this was like a little bit inspired by hybrid functionals, in which I am dependent on this S parameter that is measuring the overlap of the two densities. So whenever the overlap is significant, that means that this term is sort of like disappearing, and then we just have these terms that are what we should be expecting. But then when there is no overlap, and of course those two molecules or those two atoms are stretched, this is when the correction will kick in. And then I have grayed out this part because this part corresponds to molecules other than H2, but for H2, this is the only term that would be surviving. And here what I'm doing, I'm canceling this E-Hartree non-additive. And we do this because we know that for the first problem, the error is given mainly by the self-interaction error. So here we know that the error is mainly this. So we know exactly what to target and what we want to remove. So after we've done that, we found that we have this type of plots now in which we've managed to correct some of the behavior for each of the plots. And of course, these plots are not exactly perfect, but those, of course, are slight deviations that are due to the incorrect LDA fragment densities that, of course, affect the partition energy. And here, the idea behind these plots is this is a proof of principle demonstration that it is possible to use a simple DFA like local density approximation to fix the underlying errors that occur due to fragmentation. So now I'm gonna discuss how we can approximate the TS non-additive. So the problem that we have with this is even if we have an approximation for the EXE or E hard to EXE non-additive term, if we still want to have the linear scaling, we still need a good approximation for the TS, because of course the inversion is one of the most expensive parts of this whole calculation. And one of the things that people think about is that we can do orbital-free DFT or approximate just like TS. Obviously, this is famously hard to achieve, and of course TS non-additive is simply like a completely different challenge. But what happened is in the group, we were interested in approximating this part of the functional. We do the individual fragments exactly through the orbitals. And then what we're doing is we're trying to approximate the integrand here. And what we were trying to accomplish is just like inspired by the previous type of formulation before. Here, I'm simply combining two kinetic energy functionals. Here, I'm doing the von Weizsäcker and I'm doing the Thomas Fermi. Of course, we know that the von Weizsäcker term is exact for system with what orbitals, and then this other one is exact for the uniform gas. So what we do is we introduce these Q functions that here I'm not showing exactly because you can select different ones, but what we are interested is just in a function that has this properties that is bounded by 0 and 1, in that when in the one orbital limit we have 1, and then we have 0 in the uniform gas limit, so that each of these functionals triggers when it is appropriate to have them. Okay, and this was shown to give nice results for covalent sigma bonds. And so, of course, I've shown you some of the things that we've done to sort of like start building up on this theory, but of course, we're at an early stage still. But there is more theory to be found. Of course, we're doing the seminar based on theory. So right now what we're doing is we need to be able to gather more exact conditions to either approximate some of these functionals or approximate the partition potential. So we're hoping that with the release of the adiabatic connection, that what we do is we introduce a lambda parameter that tunes the interactions between fragments. So of course, we know that the adiabatic connection was able to gather many of the exact conditions that are used to systematically build better functional approximations. So we're hoping that this will accomplish that. And of course, we still need that kinetic functional. And another thing that is going to probably help us a lot is that currently there is an implementation within Sci4 to be able to have Pdft as a normal thing that you can apply and that you can use with regular molecules instead of just any regular system. But then in the end, what I wanted to highlight here is that our embedding methods provide a promising route to calculate things in larger and more complex systems. And before I finish, one of the main things that I've been doing lately are implementations, open source implementations, so that people can use software. So we are currently writing the manuscript for this code, which is N2V, which lets you do density to potential inversions. This is a Python code that mainly works with Sci4 and the Python wrapper, but we're also writing something that would allow you to, as long as you have any Python capabilities, you should be able to use this thing. This is done in atomic orbital basis sets. So this is code 1, and then code 2 is PyCapping, which this is based on an older code that we had in MATLAB. This is how we perform the real Pdft calculations. And in here, we really didn't want to deal with the artifacts and basis sets. So this is using prolate spheroidal coordinates so that we have errors. We have results that have no errors due to the basis set. So I hope that you can find some of that useful. And then last but not least, I just want to thank my group, and then Yuming Shi, which has co-wrote N2V with me, and Dr. Taylor Barnes, that also has been a great help in this, and then also the people who support us financially. So thank you so much again.